What follows are experiments showing spontaneous and forced imbibition at multiple rates. These green sponge pieces represent microporous carbonate grains. The space between them, when packed, is macroporosity. The space inside of one of them is microporosity, and it's highly water wet. We're looking at a pack of microporous carbonate grains. Between the grains are macropores, large, very large pores. Within each grain, as I showed you, are very, very fine, too fine to see micropores. We're going to start, the saturation is completely with gas. Air occupies all the pore space. I'm now going to start a low rate water flood from the bottom with water coming down this plastic tube. The water is colored red. The water will distribute itself between the macro and micro pores, and you can watch its progress. Notice, with very little water collecting in the macropores, it is steadily advancing ahead of the macropore water into the micropores. By spontaneous imbibition. Here's the macropore flood advance. The micropore flood advance is up here. Steady advancement through the micropores as seen here, yet the macropore flood is down here. In this low rate water flood of the gas-filled pore space, the micropore flood moves quicker than the macropore flood. Through the grain-to-grain contacts, the micropore flood is continuing to advance all the way into this grain while the macropores are here. You can see this grain filling. This grain filling its macropore space, continually advancing ahead of the macropore space here with the red water meniscus. You can continue to see the flood, both floods steadily advance. This one slowly, and the micropore flood ahead of the macropore flood. We're now making contact, capillary contact to this grain back here, and it's starting to fill with water ahead of the macropores, which are here. Now at this point, with this grain, in just a minute, I will stop the water flood. I will stop the water flood right now. The macropores have flooded this far. The micropores are up in here, across this surface here. Now notice that the micropore flood continues to advance. And now the macropore meniscus is dropping, since I am no longer adding water to the pore volume. Moving forward through the micropores and receding in the macropores very slowly according to the volume ratios of the macroporosity to the microporosity. This would continue until a gravity capillarity equilibrium would be established, dependent on the ability of these micropores to imbibe spontaneously water. I'll now restart the macropore flood slowly. And you will see the progress of two floods, a flooding of the macropore space in a flooding of the micropore space. Moving now into this grain through capillary contact, coming up through here. Soon it will establish capillary contact to this grain. And continuing. In a macropore micropore matrix such as this and such as exists in our Arab D sediments, there's two rates: the inherent rate of the micropore volume and the engineered rate that I flood the macropores. In this flood, we're going to do a very rapid filling of the macropore space with water faster than the microporosity can absorb the water. Here we go. Despite the rapid filling of the macropore space with water, the micropores are continuing to fill. The water is dropping, and air bubbles, which would normally in an oil reservoir would be oil, are coming out of the microporous grains. This demonstrates that a too rapid water flood would allow the oil coming out of the micropores to come out late and be associated with water cut production.